All right, so we're going to finish up today 7.2, and then we'll start reviewing for the test after that. So there's a little bit more to do today in 7.2, and then we'll start. We'll do some questions today. Tomorrow we'll start to review for the test on Friday. Okay, so I don't think we have this equation down, but this one you'll also want to include in your note card if you don't already have it. I don't think we went through this one. Gravitational field is lowercase g. It equals uppercase G times mass of the object divided by r squared. So this basically tells you the force of gravity that exerts on other objects. So you might already have this one down. I don't remember if you do or not, but in case you don't, you want to include that one on your note card. Did we go through this one before? Yes, that's right. Yeah, so G is the constant. M is mass of the object that experiences gravity. And then R would be, if we're talking about, here on Earth anyway, R would be distance from the center of the object to the center of Earth's core. Yeah, it would be. So that the other one I gave you was just for Earth, and you could apply this to, say, the sun, or Jupiter's surface. But yes, it's the same equation. But the one I gave you earlier was just specific just for Earth. This one, it can be applied to any place you have gravity being exerted somewhere else. Yeah, so wait, I'm sorry, did I do that? Wait, why did I write down like that in my notes? That's strange. No, I'm sorry. I was looking at something else. It's not the mass of the object experiencing gravity. It would be the bigger object. So it would be Earth, for example, I'll just say the large body that exerts gravity on the smaller object. Sorry about that. So this would be, usually it's going to be Earth, and we'd have, say, like a bowling ball would be the large or the small object that feels gravity from Earth, but we would use the mass of the Earth here. And that would tell you the force that the bowling ball exerts or feels from Earth. But it would be the mass of the Earth you put in here, not the mass of the bowling ball. So if you were looking at, you have Earth, and you want to know the field that a bowling ball feels this far away from Earth. So from here to Earth's core would be R. You would use the mass of the Earth. The mass of the bowling ball is not used in the equation. So that would not, so it does not matter. This is, we know this is true. It doesn't matter the mass that you have or the mass that an object has. Earth's gravitational field is always constant. So the things on Earth don't affect gravitational field of Earth. What Earth exerts is a constant force. And so we use the mass of that large body exerting a force on smaller objects. In this case, usually it's going to be Earth that you're going to be using. So what this tells you is that if you increase R, you're going to have a smaller G. So the farther away you go from Earth's center, the smaller G, the smaller force you're going to feel from gravity. So if you go up into a mountaintop, you will weigh less than in the valley. There's a larger R distance, you will feel less gravitational force on a mountaintop compared to being on Earth's surface. The last thing to talk about in 7.2 is different kinds of masses. So there's two kinds of masses that a physicist is going to define. So you have inertial mass, and that's usually not the kind of mass that we think about when we think about mass. The equation for that, we won't ever use this equation, but just so you understand where it comes from, it's this. So what this says is that mass inertial mass equals force over acceleration. So what they do is they exert a force on an object. They measure the acceleration of that object, and that gives them the mass of the object based on the acceleration of the object. So inertial mass is found by exerting a force on an object and measuring the acceleration of the object, which would then give them the mass of the object. Generally what they do is you can see in your book on page 183, but they have this middle blade type thing that oscillates back and forth. And so they have this straight middle blade, like a knife blade, and they attach a mass on one end. And they exert a force on that mass and then measure the acceleration, the oscillation back and forth of the blade. And that gives them the mass of the object. The other kind of mass is called gravitational mass, which you find using a scale. So it's found using a balance. And that's usually in a laboratory how we find mass. We just use a scale, divide by 9.8, and we get the mass of the object. So these are both equal and equivalent ways to get the mass of an object. Whether you find it by accelerating the object and getting the acceleration of the object to get mass, or using a scale, it will be the same mass that you get in both cases. So both kinds are equal to each other. So Newton said that gravity is a force, and he used an equation to measure the force of gravity. Einstein came along a little bit later, and he did not agree with Newton. He said that gravity is not a force. But an effect of space. Basically, what he said is that mass changes the space around it, which then seems to show a force, although it's really not a force. Yeah, Matthew? That's right. Oh, which ones? These like gravitational mass, inertial mass? No, they're not. You don't have to really know either of them, but if you wanted to use the equation for gravitational mass, it would be this right here. But you don't need to know this one, but yeah, that would be how you find gravitational mass. So what Einstein said is that mass will change the space around it. And that's what we see as gravity. But it's not really a force. And so this is what we talked about before, where Einstein thought there's a space-time fabric, and anything that has mass will warp that space-time fabric. And that warp is what we see as gravity. And there was an experiment done in 1919 that helped confirm Einstein's theory of gravity. So in 1919, there was a solar eclipse. And what Einstein predicted is that a star would become visible that was not visible before. So normally, when you have this, you have the Earth, sun out here. And when you have a solar eclipse, you have the moon coming in front of the sun right here and blocking the sunlight on part of the Earth. And so you would have part of the Earth in shadow that the moon blocks, and that's a solar eclipse. And so parts of the world are in complete darkness during a solar eclipse because the moon blocks the sun completely at that point. So it just so happens that the moon's a lot smaller than Earth, than the sun, but it just so happens that we are just far away from the Earth that the moon and the sun are the same size to us in the sky. So they're exactly the same size. So the moon looks to be the same size as the sun in the sky. So the moon can block out the sun completely because it's the same exact apparent size as the sun. So looking up in the sky at night, we see the moon, how big that is. That's how big the sun is during the day. Same exact size. Now, over time, though, the moon is getting further away from the Earth. And so years later, we won't have full eclipses anymore. As the moon will be too far away, it'll look smaller, and it won't be big enough to block out the sun's light. But for right now, we have full eclipses where we actually, it gets dark, completely dark during the day during the eclipse. Well, it wouldn't be completely dark. So over time, now, right now, yes, right now we do have it where it will be completely dark in certain places. We had one just like a couple of years back. And from, I think it was from Missouri up through Oregon, there was complete darkness for about 15 minutes or so. But not here in Texas. But the sun looked like a crescent, but it wasn't blocked out completely here. Yeah, yeah, it's exciting here. It's going to be blocked out here. So it'll be completely dark April in 2024 here in Dallas. So that'd be really cool. That was really sad. I missed the last one. We had a teacher orientation meeting that day, and so I had to be here. I would have gone up to Missouri to see it. But thankfully, we're going to have one in a few years from now. Okay, so right here, we have the Earth, the moon shadow makes this dark right here. Now, Einstein knew that there was a star back here behind the sun that we can't see. So there's a star back here. It's not visible to us because the sun blocks it. So it's like expecting to see light through this wall right here. We can't. It's solid. So we have a solid sun right here that blocks the starlight. There's no way to see the star. But during the eclipse, the star became visible on Earth. The only way to explain that is that light from the star bent around the sun and came here in which case somebody here on Earth would think that the star was right here, because our eyes will follow the path of light, and the path of light was coming from this way. It looked like it was coming from here. And so to the person on Earth, the star was right here. That's what they saw. But the star in reality is behind the sun right here. How can you see it? The only way to explain that is that the sun bent the space-time fabric so that light could then travel around the sun to Earth. That's right. Because light is following the space-time curvature. And because sun is so massive, it warped space-time fabric. Everything, including light, follows that bend in the space-time fabric. So this was great evidence for Einstein's theory that gravity is a bend in the space-time fabric. Now, we can't say it's been proven, but this is really good evidence that this is correct, and that gravity does work this way. But we still can't say for sure if he's correct or not. Einstein can't really explain why mass bends things, and he can't explain what mass really is and why it exists. So there's still incomplete parts to his theory, but it's a very solid theory based on this evidence. Because stars move around, stars don't just stay in one place. So at the time of the eclipse, it was back here, but other times of the year, it would be over here, it'd be over here. And so you can chart the star's path. And they knew at the time that it was right here. But other times of the year, it would be out here or out here, you could see it. Oh, they can chart all the stars, so they know where they're supposed to be in the sky. And based on its size, based on its color, they know which star they're looking at. So every star has a distinct color to it and a distinct size to it and location. So the main thing to know about this is that Einstein said gravity is not a force. Gravity is just a bend in the space-time fabric, but Newton thought gravity was a force. And we still to this day can't say for sure what gravity really is, but we think it's this, but it could be a combination of both. It could be both Newton and Einstein are correct, and that it could be both a force and a bend in the space-time fabric. That's a possibility too. But for now, we can't really say definitively what it is. Okay, well, that's the end of 7.2. Let me give you some things to work on before class ends today. Just a few questions. On page 185, do 15A, don't do B, 16, 19, and 21. Yeah, so do 15A, but not B, 16, 19, 21, page 185. I'll give you the other questions to work on too for tomorrow and on Thursday. The chapter review questions, if you want to do those, you can. Yes.